That's a very important. All right, so we were talking about just the basics, and it's been a while, and you guys had a test, so we're going to go over a little bit of the stuff that we did before. So we were talking about muscle attachments and muscle actions, and we're going to really get into muscle actions today and hopefully give you a really good understanding of how these things work. So what I told you guys last time is that muscle has at least 2 points of attachment, right? And often they are called the origin and the insertion. Sometimes they just call them generally muscle attachments. And remind me what the difference between an origin and insertion is. Somebody explain. Huh? Fixed or immovable, right? And the insertion is the one that wiggles when you contract it. And generally, the action is to bring the insertion closer to the origin, right? At least the most likely action that you're going to run into is to bring the insertion closer to the origin. So with that in mind, what we're going to be working toward is if you see the attachment points, you can figure out what the action should be, yeah? Or if you see the action, you can figure out which attachment point should be which, right? So the muscle attachments, the origin and the insertion. So just generally, this is the biceps brachii muscle. It's got 2 heads. We'll talk about that, and they share a common attachment point. And you are going to contract the muscle and bring the insertion closer to the origin. And remember, as far as the physics goes, muscles only pull, they never push, right? They pull, and then they relax back to their original length. And so what we talked about last time was that, therefore, if I have a joint and I want to be able to do 2 opposite actions at the same joint, I need to arrange muscles in pairs around the joint, right? So if the muscle that does this is here, where's the muscle that does this? Right, exactly. It's going to be on the back. So muscles are arranged in what we call opposing or antagonistic pairs. And the opposing or antagonistic pairs around the joint. So if I look at a muscle action, and I say, okay, there's this action, the muscle that does the opposite of it would be considered the antagonist to that muscle, right? And you know enough literature to know that the antagonist is generally working against the hero. So if I define this action as the one that I'm talking about, the muscle that does it is the agonist, sometimes called the prime mover, and the muscle that does the opposite is the antagonist. Now, I'm not saying that you can look at any joint and say that's the agonist and that's the antagonist. You have to talk about one movement versus the other, right? So if I'm talking about this movement, then the antagonist is the one that does that. Yes? Okay. But sometimes the agonist doesn't work alone. It has a helper. And if you have a helper, it's called the synergist. Okay, so let me give you an example. The action that I'm going to do right here, closing the jaw, elevation of the jaw. The muscle that does it, we talked about it last time. Tell me where you think the origin is approximately. Origin should be up here and insertion should be down here, correct? Okay, so that's the agonist. Okay, it has a helper, and the helper gives it more range of motion. It's not as thick or as strong. Its origin is up here and its insertion is down here, and it gives it more range of motion. Why is it not considered the agonist? Because this one has more of the action, does more of the strength of the muscle movement, and this can add to it. Does that make sense? So this would be considered the synergist. Okay, so this muscle goes here to here. Now, something conceptually interesting and also important. If a muscle wants to have a similar or the same action, they don't really have to share their origin, but they do have to share their insertion, don't they? Does that make sense? Okay. So for instance, I have a couple of heads of the biceps brachii. They do slightly separate, slightly different things, but they're going to share at least one of their actions if they share the insertion. Does that make sense? Got it? Because what you do is you pull the insertion closer to the origins. So if the origins are close to one another and the insertion is the same, then you can have overlap of actions. Does that make sense? Okay, so we've got agonists and antagonists and synergists. I don't expect you to memorize that, but if I showed you a motion, for instance, if I showed you this, and then I said, tell me the muscle that is the antagonist to that muscle, eventually you'll be able to figure it out, right? You'll be okay. This is an action she's looking at. This would be the opposite action. What's the muscle that does that? Does that make sense? So that's how you use those terms. You don't use memorization. You're like, I'm looking at it and figuring out what the opposite is or what the synergist. Okay, likewise, when you're doing flexion at the elbow, which we'll talk about, the prime mover that does most of it, actually people argue, there's two muscles that help with it. There's the biceps brachii, and then there's the helper, which is the brachialis. They have two different origins. So the biceps brachii has origins up here and insertions down here. The brachialis has origin up here and insertion down here. But they do something similar. Does that make sense? So they're working together for that action. Okay, so specific terms for muscles are going to be based on body movements. For instance, some muscles will be called flexors and some will be called extensors. But what we have to get down and we're going to do now is when you are talking about muscles, to flex a muscle anatomically does not mean the same thing as it means in the gym. Okay? Flexion means something specific, extension means something specific, abduction, adduction, they all mean something specific. So what we're going to try to do today is to get our sort of common assumptions, just like we did with that first set of notes in which we were like, okay, we always assume we're in anatomical position, and we know that dorsal is this side and ventral is that side. So that's what we're going to do today. We're going to learn what flexion and extension mean, and then we'll start learning specific muscles as we move through. Okay, so Chapter 9, it has joints. We already did part of it, but the other part of it is body movements. And the body movements that we are going to do, most of the body movements that we're going to be doing are going to be body movements at synovial joints. Because what can you tell me about the mobility of a synovial joint? They're the most mobile, right? Some of these actions will also happen at cartilaginous joints, like here. This is cartilaginous, it's got fibrocartilage, right? Okay. But really, none of these motions are going to refer to fibrous joints. That makes sense? So we're going to be looking at synovial joints mostly, and then also a little bit of cartilaginous joints, but not fibrous joints. Okay, so these body movements are going to be directly related to that column of your muscle tables that is called the action of the muscle. Okay? So that's what we're trying to accomplish. When you look at that action of the muscle column, you can just rote memorize it, but it won't stay with you. And I know because that's how I learned them, and I had to freaking relearn them when I started teaching them. I was like, okay, well, how can you make this make sense instead of just memorizing and doing a brain dump for the test? So that's my objective, to make it make sense to you and to make it logical to you so that you can pull it up for long periods of time. So the body movements allowed by synovial joints, at least mostly. This is the connection between the skeletal system and the muscular system. And these are going to be directly related to those muscle actions. So the first one is that this one is not an angular movement. I'll just describe angular movements in just a second. This one is a gliding movement. I'm not dramatically changing the angle between the carpals, but I'm moving them with reference to one another, right? That's called gliding. You can do the same thing at the tarsals, not dramatically changing. But most of the movements you do at your limbs are dramatically changing the angle between the bones, okay? So this is a gliding movement. You're not going to see a whole hell of a lot of that. And then the rest of them that we're going to be looking at, most of the rest of them are going to be called angular movements. Angular movements will change the angle between two bones. So look, you have to look at the angle from anatomical position, and it's easy. But what's the approximate angle here? 180. So this is changing the angle, do you agree? And this is putting it back by changing the angle. Does that make sense? Okay, so first thing we're going to do is talk about flexion. And when you talk about flexion anatomically, it specifically means that you decrease the joint angle between two bones starting from anatomical position, okay? So this would be flexion, yes? Decreasing the joint angle, okay? So this is anatomical position. You're at 180, 90, less than 90, right? 45, can't go all the way up to 0, but I'm close to the way, okay? So this is flexion at the spine. Is that okay? Actually, that's flexion at the hip. This is flexion at the spine, okay? This is flexion at the spine. Okay, so this is flexion, extension, okay? This is flexion at the hip usually means you're going this way because you're moving the thigh. You can do it the other way too, but we're not going to define that because that is a little harder for students. So this is flexion at the hip, right? Okay, now this is flexion at the wrist. That makes sense? This is flexion at the neck, okay? And then the knee is a weird one because the knee cannot flex anteriorly, okay? we remember are derived from quadrupeds, and then this anatomy makes a lot more sense. But with us, the flexion, the only flexion that can happen at the knee is this way. It's still decreasing the joint angle from anatomical position, right? So it's consistent. Okay, so decreasing a joint angle, it generally brings two bones closer to one another. And so let's look at a couple of animations about that. So when you look at this animation, I want you to ask yourself a couple of questions and see if you can figure them out. By looking at the animation, I want you to tell me which joint is primarily being flexed, okay? And then I want you to tell me where you think the origin is with reference to the insertion. Which one's which? You don't have to give me specific bone markings yet. You will get that later. Okay. So which joint is primarily being moved? The elbow joint, exactly, right? And where is the origin with reference to the insertion? So the origins are up here, and the insertion is down here, correct? Okay, now remember the rule that we said you have to cross a joint to move a joint, right? So I don't want you to get into the habit of telling me that something moves to the elbow and inserting it actually up here onto the humerus. Doesn't make any sense. Does that make sense? Now, don't be at all surprised if things happen that are slightly counterintuitive. Like, for instance, if you have a muscle that crosses two joints, the action that will be one of its prime actions will be to move the one that has the greatest strength and range of motion, right? So it's going to be move the elbow joint. But if you see it crossing two joints, it may have some slight action at another joint. Does that make sense to you? Okay. And I'm going to reinforce that as we go through. Now, I'm not telling you those so that I'm giving you more to memorize. What you're responsible for memorizing is the table of muscle actions that's in your lab book. I wrote it. That's what I'm going to hold you responsible for. When I'm telling you stuff like this, I'm trying to give you a conceptual understanding of what muscles are actually doing, not holding you responsible for more minutia, okay? So, and we'll talk about that with a couple of different muscles. Okay, so that is bringing two bones closer to one another. And then this one, okay, I want you to look at this one. Ask yourself the same question, same questions. What joints or description of what kind of movement's going on, and then where's the origin with reference to the insertion? This is also flexion. Okay, so what are you moving? Yeah, the ribs are actually staying put. Yeah, you're moving the spine. You're doing anterior flexion of the spine. Sometimes they call it flexing the abdomen, just because it looks intuitively like you're flexing the abdomen. Where's the origin with reference to the insertion? Where's the origin? The origin is down here, right? Close to the pubic symphysis, right? And the insertion is all the way up ribs to sternum. Does that make sense? Okay. Now, when you look at this muscle, very often people want to flip the origin and the insertion, and I think the reason that they want to do that is because most of the time when you're dealing with your limbs, the origin is closer to the trunk than the insertion is, or more superior. Does that make sense? So they a lot of times get this one flipped. Now this muscle can do a little bit of the opposite, but that's not its primary action. It can pull your hips up a little bit, but its primary action is to do this. And you've got a lot more strength moving that direction. Does that make sense? Okay, so you guys tell me, based on what you've just been looking at about flexion, where do you think you should expect to find flexors on most joints? Which surface? Everybody come up with it. Anterior surface of the joint, generally speaking. Now, for those of you who have been to lab this week, you've probably encountered the damn forearm muscles. And the damn forearm muscles include a group that's on the anterior surface, some of which are flexors. The flexor carpi ulnaris, the flexor carpi radialis, right? So the flexors are going to be on this side. If you're labeling something a flexor on the posterior side, you are not understanding the action. Does that make sense? So the flexors are going to be on this side. Now, they're not always named flexors, but if you have something that's a flexor, usually you're going to find it on the anterior surface, with the exception of what joint? What's the exception? Yeah, the knee. The knee flexors are on the posterior surface. But something that is responsible for instance, flexing your neck should be here. Flexing your vertebral column should be here. Flexing your hip should be here, right? Flexing your wrist should be here. Flexing your elbows should be here. Where's the one that's flexing your shoulders? It looks like these are confusing, but just imagine that this plane keeps going, right? And that's flexion of the shoulder. Does that make sense? So generally, you're going to find a muscle responsible for flexion on the anterior surface with the notable exception of the knee. The knee does not have flexors on the anterior surface. Is that good? Okay, so now let's talk about extension. Extension is generally replacing something after you flexed it. It's usually replacing it to anatomical position. And they call it increasing the joint angle, but it doesn't mean you're increasing it past anatomical position, right? If you're going from a flexed position back to an extended position, you're usually replacing it or straightening it, okay? So it is the opposite or antagonistic movement to flexion. And so if I find flexors on the anterior surface, where do you think I'm going to find extensors? Usually on the posterior surface, right? So your elbow flexors are going to be on this side, your elbow extensors are going to be on that side. On the wrist movement, your wrist flexors are on the anterior surface, your wrist extensors are on the posterior surface. Does that make sense? Your knee flexors are going to be back here, and your knee extensors are going to be up here. That make sense? Okay, so let's look at extension. Okay, so I want you to look at this. I'm going to ask you one more question with this one. Same start, which is what joint or joints is this moving? And then where's the origin with reference to the insertion? And then the third one is what muscle is this an antagonistic movement to? What muscle is this working against or working in opposition to? Okay, first question. What joints are you moving? Yeah, you're doing the spine. If this was flexion of the abdomen, then this is extension of the abdomen. You can do hyperextension at some joints, but not all. So if you go past anatomical position, flexion, extension, hyperextension, flexion, extension, hyperextension. You can't hyperextend the knee, at least on purpose. You can at the hip, flexion, extension, hyperextension. Okay? So the second question is where are the origins with reference to the insertions on this one? Where are the origins? The origins are lower and the insertions are higher. Okay, these muscles are actually three different groups of muscles. They're called the erector spinae muscles. And what they do is they're kind of sequentially inserted onto the ribs so that when I bring up my spine, I don't just do this. I can roll it because I've got a sequential, right, insertion points. Does that make sense? So your origins are staggered and your insertions are staggered all the way up to your cervical spine. Does that make sense? So those are the erector spinae muscles. And looking at this, what muscle do you know that this one would probably be the antagonist to? Rectus abdominis, yeah. Does that make sense? Okay. All right. So generally, you'll find muscles responsible for extension on the posterior surface of the joint, excepting the knee. Good? Okay. So that's going to be really useful. If you guys are anything like me, these are going to be the hardest groups of muscles that you've got. Okay? So when you're looking at these muscles, there are some things that I want you to know, not just for these muscles, but for other muscles as well. The body of the muscle, the sort of meaty part of the muscle, where it lays and how big it is and how wide it is pretty variable, okay? So, and also once you cut a cadaver there, sometimes it'll get stretched a little bit, so it'll be slightly lateral when you expect it to be medial. But what's really dependable is the attachment points. Because if you had a different attachment point, you would have a different action, right? So where is the safest place to identify a muscle if you can? You find the tendon and you follow it up, right? Okay? Because if I have muscles that are flexors, the attachment, if it's a flexor carpi radialis or flexor carpi ulnaris, it should be on the anterior surface, right? Okay? And the flexor should be here. An extensor should be on the posterior surface. Does that mean that the muscles can't get flopped around up here? They can. So what you need to do is you need to follow the tendons and then find the body of the muscle. Always use the tendon as your sort of orient because it's going to be in the same place relatively, right? And And it's going to be relatively similar in size, too. The tendons don't change in size dramatically. So, for instance, I can't work out and make my tendons dramatically larger. I don't stop working out and my tendons shrink dramatically, right? But the muscle changes pretty dramatically in proportion as you use it. So use your tendons as your identifiers. Now, I understand with some tendons, they're harder to find, but follow them as far as you can, and then follow them back up to the muscles. So, generally, you're going to find muscles responsible for extension on the posterior surface. Okay, now abduction and adduction. Abduction and adduction are moving things toward or away from an imaginary midline. So let's use imaginary midline as my midline of my body. When you abduct, like to kidnap, you take it away from the midline. Okay, abduct. Okay. When you adduct, you add it back. Abduct, adduct. So I want to think about the physics and the architecture of the muscles. And so if you're going to abduct, yes, you should probably find muscles responsible for abduction on the what surface of the joint? Lateral surface of the joint, right? So the muscle responsible for abduction at my shoulder has my origins here, my insertion here, yes? Okay? And what you do is pull the insertion closer to the origin, and that is abduction. Does that make sense to you guys? Okay, so I'll show you a video of abduction. It's pretty easy to tell the origin and the insertion. Okay, so you see what it's doing? Okay, so the origins you will figure out are the clavicle and the scapula, and you'll specific points on the clavicle and scapula. And the insertion is actually the deltoid tuberosity of the humerus. Eventually, by the time you have the confidence and time to organize your knowledge, it'll start to be a single story instead of bones and then muscles and then nerves. But it takes a while before it gets there, so do not expect it to be there yet. Go ahead.
So I thought it would be the origin would be here because it's, you know, you're kind of
no, well, think about that. If the origin was here, I want you to just think about that physics. If the origin was here and the insertion was here, what you would be saying is that this stays stationary and I pull my entire torso toward my humerus. Does that make sense? Okay, that's what you would be saying if you flipped the origin and the insertion. And so if you can try that out, you can see that one makes more sense, way more sense than the other. But you can kind of understand how you think, oh, well, yeah. It's a little hard to figure out what you're saying is stationary versus mobile until you play around with your body a little bit, right? Flap your arms. So where do you think the muscles responsible for abduction at the hip are located? Here, right? They're on the lateral surface. Yeah? Okay? That makes sense? Okay. Huh? Here. Yeah. Like the tensor fascia lateral and then some other ones that you haven't learned yet. But there. So this, by the way, don't let this confuse you, but this, if I'm using my hand, then the midline, the imaginary midline is right there. So this is actually abduction of the digits, right? I'm abducting the digits and then moving them back. Abducting, adducting, abducting. Okay, with that in mind, one of the muscles you're going to have to learn this week, and it'll take a little while to get it, is the abductor pollicis longus. Okay, so tell me what that is trying to tell you. Where is it? It's abducting the pollex, the thumb. So where do you expect to find the muscle? It's going to be on the lateral surface over in here. I'm not going to be looking for it over here. Okay. And think about this for just a second before we go any further. If I have an extensor pollicis, a flexor pollicis, and an abductor, I want you to see if you can predict how I would run into those tendons. Where should I run into the flexor? If the three tendons are right next to each other, and they are, where should I run into the flexor? Anterior, and then moving it around, what should I run into next? Abductor, and then? Flexor, abductor, extensor, right? Do you see how knowledge of the actions can help you figure out what to expect when you're actually looking at the cadaver? It's really useful, right? Because then it's not rote memorization. It's like, oh no, the extensor should be posterior, and the flexor should be anterior, and then between them should be the abductor. But if you keep following the muscles up, sometimes they'll get flipped around. That's why I don't want you to only look at the bodies of the muscles, because they're all long and skinny, and if students pull on them enough, you can have the flexor be lateral to the abductor, just because they yanked on them for a while. So you look at them down here instead, and then you follow them up. Okay, so now let's do adduction. Adduction is adding it back. And so if your abductors are lateral, then where do you expect your adductors to be?
Medial.
So I'll do adduction at the shoulder. This is adduction. Although it's counterintuitive, if this was abduction, this is adduction of your fingers. That one's a little hard. This is abduction at the hip, and this is adduction at the hip. Yeah? That makes sense? This is not abduction and adduction. There's special names for it with your neck. So, like abduction and adduction. So muscles responsible for abduction at the hip are on the lateral surface, and the muscles responsible for adduction are on the medial surface, and they're actually called adductors. Right? You've got an adductor longus. What else do you have? Have you done them yet? Magnus. And brevis. Yeah? Okay, but based on their size, and we'll talk about that meaning later. Does that make sense to you guys? Okay, so this one's a little confusing, though, because you have an obvious deltoid on this side, and it makes a lot of sense that that's an abductor, but you don't really have any muscles right here. So the muscles that are responsible for adduction here are not right here on this medial surface, but it'll still work because they're here to here and here to here. That makes sense? It's still medial, yeah? And the physics still works on it, right? It's just not right there. Okay, everybody okay with that? So those are abductors and adductors. And now, let's talk about circumduction. And circumduction is this movement, and it's a complicated movement, in which, primarily at ball and socket joints, because it's called something different at the neck, you take a limb and you make a cone in space, right? Okay, but really all circumduction is a combination of 4 actions. So if you look at circumduction and you're doing this, I'm going to do it and I want you to tell me which actions I'm doing. Flexion at the shoulder, abduction at the shoulder, extension at the shoulder, and adduction. So that's all circumduction really is. And you can do the same thing at the hip, although not quite as gracefully, right? Do that there. So that's circumduction at the hip. And in order to do circumduction, of course, you're going to need muscle all the way around. Flexors, extensors, abductors, and adductors. Is that okay? Okay, so that's circumduction. And then rotation. Okay, so rotation is specifically taking a bone and rotating it around its own axis. And this is hard to show, but it's easier to feel. So I'll show you, and then I'm going to ask you to do it. So specifically, this is the figure they show, but it's kind of counterintuitive what they're trying to show you. So this is the figure they show for lateral and medial rotation here. But it looks like they're moving the elbow, and that's not what you're supposed to be doing. So what I want you to do is to hold your body in anatomical position, okay? And then I want you to take the humerus. It's going to feel like you're moving this, but you're not. Take the humerus and laterally rotate it so that you get a good stretch across your chest. That make sense? Okay? And then put it back in anatomical position. And then medially rotate it so that you get a good stretch across the top of your back. Okay? That's lateral and medial rotation. Does that make sense to you? Okay? So now it doesn't really matter what I'm doing here, right? Because the muscles that are doing it are really moving the shoulder joint. It looks like you're moving here, but don't let that distract you. So you're moving your shoulder joint laterally or medially. Good? Okay? You can do lateral and medial rotation here as well. It's easier to understand here. But I want to talk about this lateral and medial rotation. You can also do it here, but the hip has way less lateral and medial rotation flexibility than the shoulder does. Okay, so I want to think about the physics of the anatomy of lateral and medial rotation, because if you can get this one, it kind of means you have the story down. So with lateral rotation, what I'm doing at the shoulders, I'm going from anatomical position and I'm moving it back. So I want you to see if you can figure out where the attachment points should be for a muscle that does that. Where should the origin be? Where should the origin be? Good. Where should it be? Yeah, it's going to have to be on the posterior trunk. Do you agree? Somewhere on the posterior trunk. And where should the insertion be? It's not going to be up here. I'm trying to move. Yeah, it's got to be on the limb right here. And depending on where it inserts on the limb, will give you more or less range of motion. If I just have it right back here, then I don't get very much range of motion. I have it inserted all the way up here and get more range of motion. That's kind of the difference between these two, the insertion points and the mobility of the muscle. So in order for a muscle to do lateral rotation, you would need an origin on the posterior trunk and an insertion on the limb. That make sense? Okay, so that's lateral rotation. Can you think of any muscle that meets those criteria that would probably, even if you haven't memorized it yet, be responsible for doing that? Origin on the trunk, posterior, insertion on the limb. Good, latissimus dorsi. Yeah? Those strap muscles that go here to here. Yeah? Does that make sense? Okay, that's not all they do, but that's one of the functions. Does that make sense? Does it also surprise you that the latissimus dorsi, if their origin is here and their insertion is here, in addition to doing lateral rotation, they can also help with adduction? Yeah? Okay, that's what we're working for. We're working for looking at the muscle and understanding the actions of the muscle, right? Okay, and then eventually you'll be able to work backward, action to attachments. Okay, so that's lateral and medial rotation. You can also do it at the head or at the neck. So medial rotation, if we're going to do medial rotation, we're doing this. So if you got lateral rotation, you can get medial. Where should the attachment points be for medial rotation? Origin, anterior trunk, and insertion onto the limb. Yes? Okay. So for instance, can you think of a muscle now, if I said the latissimus dorsi was one of the muscles that was responsible for lateral rotation, can you think about an antagonist to that function in the latissimus dorsi? Pectoralis major, yes. That make sense? Okay.
Does the deltoid also have
a little bit, yeah. One of the wings of the deltoid can help with that, help with each one. So that's when they get into like these other functions. So usually when we give you that table, we're trying to give you its primary function, not like its all-inclusive function. So the reason that that's important is because, for instance, if you go on Wikipedia or if you go on a med school anatomy page, you'll have a lot more functionality listed for each muscle. It's not like I was trying to lie to you. I'm trying to limit it so that you can actually get the structure-function relationships and then you can add to them later. You can say, okay, well, the deltoid, if you move this way, it does abduction, but if you only use the anterior portion, it can add some other functionality. If you only use the posterior portion, it can add some other functionality. And conceptually, that stuff is all really interesting, but I don't want for everybody to fail anatomy. I don't. I would really like for you guys to be able to do this. Yes. Okay, so medial rotation. You often find muscles responsible for medial rotation with an origin on the posterior surface of the trunk and an insertion on the limb.
So when you say
that makes sense?
Muscles that help, that would make them the synergists?
Yes.
Okay.
Mm-hmm. Mm-hmm. So for instance, if with your question, even if the deltoid ended up having some functionality associated with medial rotation, it wouldn't be the prime mover for medial rotation.
But it'd be the synergist.
It would be one of the synergists for medial rotation. If you're going to be the prime mover, you need to have some range of motion and some of the body of the muscle. So if you just think about the physics, if you're pulling on something and you only have it that far apart, you're not going to get much strength in the movement, right? But if you have the origin and the insertion further apart, it's like trying to pick up something. If you're trying to pick up something heavy, you don't start from here, right? There's like and it's not from here either, but there's a certain angle at which it works really well. Okay, so other movements. Okay, these movements, the first two are really specific, supination and pronation. Supination and pronation are exclusive to radius and ulna. It just only means this one thing. And remember that the radius and the ulna have the interosseous membrane between them that sort of holds them in position with reference to one another. And whereas, go ahead, did you raise your hand? No. Okay, whereas the humerus, if I'm doing this, I'm kind of rotating the humerus around its own axis. The radius and the ulna, I can rotate sort of around one another, okay? So what you're going to do with supination and pronation is now I'm not concerned with the elbow joint at all. I'm going to try to hold it still. It's going to look like it's a wrist movement, but it's not a wrist movement. It's actually, the motion is actually happening right here. So what I'm going to do is I can actually take the thumb and put it medial, take the thumb and put it lateral, okay? But what you're really doing is you're crossing the radius over the ulna and then you're making them parallel again, and you're crossing them and you're making them parallel again. So which one is which? Supination, the way I learned it, it's ridiculous, but it's worked for a while. If you supinate, you end up being able to drink soup. And if you pronate, you po it out. Okay? I'm from Texas, so we po things out. So you supinate and you pronate. Supinate, pronate. And what I want you guys to do is, instead of me telling you how the anatomy of the pronator teres, which is there, or the supinator, how the anatomy corresponds to the functionality, what I want you guys to do is to, when you're looking at the supinator and the pronator, look at the attachment points and see if you can figure out how it would move something like that, right? So that's one of the harder ones, and I want to just discuss it with you next time, because some of you guys haven't been to lab yet, right? You haven't been to lab and you haven't seen the supinator and the pronator teres, okay? So I want you to look at it and see if you can figure out how the physics would make it move, okay? All right, so that's supination and pronation. And now, these movements are special to the ankle, well, mostly special to the ankle, and they are called dorsiflexion and plantar flexion. And the problem with these is that they should have named them a flexion and extension, but they're both flexion, and it confuses everyone. But we can make it make sense. So dorsiflexion and plantar flexion, and then eversion and inversion are motions at the ankle. So in order to see these, just stand up here. So dorsiflexion and plantar flexion. Where's the dorsal surface of your foot? Top. And this is the plantar surface of your foot. So if you flex toward the dorsal surface of your foot, like trying to take your big toe and touch your shin with it, okay, that would be dorsiflexion. Okay. Before we go any further, I want you to tell me the approximate location and maybe attachment points for a muscle that would be responsible for dorsiflexion. Where should it be? Where should the muscle be? It should be on the anterior surface. Do you agree that if you can't insert it here, you have to cross the tarsal bones, right, in order to move that joint, right? Does that make sense? So that's dorsiflexion. The muscle should be on the anterior surface of the shin, the tibia, and it should cross the tarsal bones in order to do dorsiflexion. Does that make sense? And if you do plantar flexion, if you're standing up, it would make you stand on your tiptoes, yeah? Because you're flexing toward the plantar surface of the foot. But if you're not standing up, you can actually point your toes like a ballerina, right? Okay, so where should the muscle responsible for plantar flexion be? Posterior surface, okay? And it has to go past the tarsal bones to move the tarsal bones. And if you want some range of motion, you shouldn't stop here on the calcaneus. You should insert on the bottom of the calcaneus, right? That makes sense? You guys remember the calcaneus, right? Good? Okay. So what's the muscle responsible for plantar flexion? Do you know one of those muscles back there?
Soleus.
Soleus is good. There's an even better one. Gastrocnemius, yeah. Okay, so let's look at the plantar flexion. So you should be able to tell by looking at this. I don't know what the hell they're doing up there. Where the origin and insertions are for plantar flexion. Let's go back to here. I hope nobody's getting killed in there and we're just sitting here. Good? So the origins are up here, and this is a little weird. So this means that the gastrocnemius, because the insertions are further up than you would expect them to be, so they're actually not on the tibia, the origins are not, they're past the knee joint. That means that that muscle might have some counterintuitive functionality. Does that make sense? So yes, it will make total sense to everybody that it does plantar flexion, but if you ever see that it does something at the knee, don't be surprised, because it crosses the knee and it crosses the ankle, yeah? Okay, but you can tell by the physics which joint it's primarily going to move, which would be the ankle joint. Does that make sense? Okay, so that's dorsiflexion and plantar flexion, and then eversion and inversion. Those are more subtle movements, so it's kind of hard to see actually. Eversion and inversion would be taking the sole of the foot. Eversion would be pointing it laterally, okay? and laterally. So you just take the ankle and you sort of take the plantar surface. It's not a dramatic movement. And pointing it medially, right? That's inversion. So you should be able to figure out with that where the muscles for eversion and inversion should be. Where should the muscle be for eversion? Lateral surface of the foot. And if you wanted it to have some range of motion, you'd have to insert it way onto the bottom of the foot, but it doesn't. So it doesn't have much range of motion there, right? So eversion goes laterally, and inversion goes medially. And inversion, the muscle is here, right? That makes sense? So that's eversion and inversion. Okay. Before we get to jaw movement, I want to tell you something that I had the hardest time with because, like I said, I memorized and didn't understand when I was trying to do this stuff. So I have a group of muscles. They're called the quadriceps femoris group. And they go, the origin is all the way up here, at least for some of them, and then across the hip. And then they share a common tendon that also crosses the knee. So I have this group of muscles that when you start reading them, you will see that it does things that look like they don't make a damn bit of sense. For instance, it will tell you that these muscles, or at least some of them, will flex the hip. But what will they do to the knee? They extend at the knee. So does that make sense? Or the other way it's written is that they flex the thigh, yes, and they extend the leg. So here's where you have to remember that thigh and leg mean very different things anatomically. This is the thigh, right? And to move the thigh, I generally use the hip joint. But this is the leg. This is not the leg. Yeah? Okay. So can you see how a muscle that crosses both of those joints on the anterior side might be able to flex the thigh, yes, and also extend the leg? Okay. That's what I didn't understand when I was looking. I just tried to memorize this, and I'm like, what the hell? You just told me it flex, and now you tell me it extends. I'm just going to memorize it, and you can't make me learn it. So it was years before I actually learned how that made logical sense. But that's because it crosses those two joints. Okay? All right. So jaw movements. So when we're looking at jaw movements, some of them are really easy. Actually, let's do it without the jaw first. Let's do, where is it? Oh, elevation and depression is a jaw movement that you have at other places as well. So it's pretty logical. If you elevate something, you're generally going to move it superiorly, and if you depress it, you're going to move it inferiorly. So if I do this, elevation, depression, elevation, depression. It's like they didn't realize they were in college, really. Like, I wonder what people are doing right now. No. Okay, so if I'm doing elevation, what bone am I primarily moving when I'm doing this? Scapula. Scapula. Okay. Now, where do you think a muscle that would elevate the scapula might be attached? Origins and insertions. Where should the origin be approximately? Has to be superior to the, right? Has to be superior and posterior. And the insertion will probably be maybe the spine of the scapula. Okay? So you have supraspinatus. It wouldn't be inappropriate to think that one could be responsible for elevation. It's on the top of the spine of the scapula. And depression. Depression, where should that muscle be? Going to near the scapula. Yeah, it should be below the scapula, and the insertion should be below, and the origin should be below, and the insertion should be on scapula. Does that make sense? Yeah, elevation and depression. Okay. Okay, so how about elevation and depression of the jaw, because it's really easy to see at the jaw. Elevation and depression, oh, they didn't put it on there. Elevation and depression, it's really moving the mandible primarily. So elevation, depression. Elevation, depression. Okay, so you already did this one, but tell me again. Now that we can use the right word, elevating the jaw, where are the attachment points? Where's the origin? Zygomatic arch, yeah. And the insertion? Onto the mandible. It moves the mandible. right? Okay, and that's how it's actually going to do that. Okay, got it? Okay, the platysma, I'm sorry, not the platysma, the temporalis will help. Very thin, though. It doesn't actually provide most of the force of the movement. And the muscles responsible for the opposite should be where? No, it's not. It's one that you don't know, but where should the muscles be? What do you think? Where should the origin be approximately? Just trying to pull it. Yeah, there has to be down here somewhere, all right? And the insertion onto here. Does that make sense? You actually don't learn those muscles. You learn the only one you learn here is you learn here. The platysma and the sternocleidomastoid. Platysma is really thin and does this. Just kidding, huh? And then there's the sternocleidomastoids. There's a whole bunch of muscles called the neck strap muscles that we actually don't teach you guys because they're really freaking hard. So, but there are other muscles that you're not learning, just like there's other tissues that you're not learning. So that's elevation and depression. And then the other thing that you can do at the joint, at the jaw, is protraction and retraction, protraction and retraction, if you want to be extreme about it. Protraction would end up being with an underbite. It's moving that mandible forward. And retraction would end up with an overbite. Okay? And chewing, do you agree, will involve all four of those, right? Elevation, depression, protraction, retraction, right? That makes sense? And we can do all of those because, of course, we have a hinged jaw, which was a big evolutionary step. I don't know if you guys know this, but there are vertebrates that, like the lamprey, that have a big open mouth with no hinges, which means the only thing that they can eat is the things that fit in the hole, right? But the development of a hinged jaw was enormous in the development of vertebrate, because now I can eat any damn thing I please if I am persistent and can catch it, right? I can eat an elephant if I've got a while, right? Okay? So the hinged jaw was really big evolutionarily to develop. Okay. And then the last movement, not the last one that you're going to run into, but the last of the major ones, is called opposition. And opposition also was tremendously important evolutionarily. Opposition is taking your thumb and being able to touch all of your digits with your thumb. This is like opposable thumbs. That's what they're talking about when they say opposable thumbs. And we're not the only ones to have it, but one of the few that have it. We've got opposable thumbs. This gives you tremendous capacity for digitally manipulating things. And there are some primates that have a hand that looks very similar to ours, but they don't have opposable thumbs. They can do this and they can do that, but they can't do this, right? So this, in combination with the hinged jaw and the huge brain, is the reason we've got the inversion right now. Okay? If it was dolphins, they would have figured this shit out a long time ago. Yeah, pretty sure. Their problem is no opposable thumbs, and they haven't been able to get around it. One of these days, though. Okay, so that's opposition. All right, everybody okay? Okay, so the idea that I would like, and I realize it's going to be a little while, usually the first week in lab when you're doing muscles, all you can do is try to identify them. You can't quite get to the point that you start to try to understand them yet. And then the next week, you can have a little bit greater understanding, and then you have your muscle list for next week is easier than it is for this week. That's why I flipped them. That's why I do appendicular before axial, because then it gives you 2 weeks to work on appendicular, right? And you can do axial at the same time the second week. So by the time you get into the second week, then you can start thinking about actions and attachments. It's just, you just cannot do it all at once. So what I want you to do is to start thinking about that. And then when I give you a quiz, which won't be until next Thursday, a week from today, how will I ask you this kind of stuff? Well, at first I'm working on you guys understanding the physics and the logic of muscles. So instead of asking you things that I expected you to memorize, I will ask you, if I have a muscle that's attached at these 2 points, tell me a logical action of that muscle, right? And if I put it on the anterior surface and tell you extension and it's not the knee, or abduction or adduction, you're like, no, it's not going to do that. Or if I have it move a joint that it doesn't cross, right? You say, isn't that, right? Does that make sense? Or if I do it the other way, if I tell you the action and then ask you which one of the attachment points is the origin or the insertion, right? So the first set of quizzing is, do you get the understanding of the physics? And then the second set will be, now I'm going to ask you specific muscles that you've already been learning in lab. Does that make sense? So that's kind of the way that it was successful for me to learn it. Get the plan, get some examples of the plan, and then start putting the specifics into the examples of the plan. So that will be next Thursday, your first muscle quiz. Everybody good? Okay. Any questions? No? For real? No questions? Did I forget anything? Okay. So the next thing is also related to the muscles that you're doing in lab. I want to teach you how the muscles are named, because sometimes the name can really help you figure out the anatomy. Sometimes it doesn't, but most of the time it does. As far as muscle terminology goes, there's some prefixes and roots. Sarco means flesh, and it's usually used to refer to microscopic or submicroscopic muscle structures. So once we get into the last part of this set of notes, when we start talking about muscle physiology, then we'll be using that prefix a lot. Myo, or MYS, the suffix MYS, or even the root MYS, means muscle, and a lot of times you see it used for gross anatomy. So anytime you see those things, that's what they mean. And remember that a muscle fiber is the same thing as a muscle cell. Yes? Okay, so they use those terms interchangeably in these chapters. Okay, so let's talk about how skeletal muscles are named and try to give you some examples of each one. Okay, so unfortunately, they did not get their crap together when they named skeletal muscles. There was not a single naming convention, right? So what it is like everything else in languages. You just get a whole bunch of historical relics that are in there, and from different languages and different time periods. But the best I can do for you is to sort of give you an understanding of when you see a muscle, figure out why it's called that, because that's helpful. Okay, so sometimes muscles are named by their action, like we said. So you do have flexors and extensors, and you do have abductors and adductors. You have levators, pronators, and supinators. Does that make sense? So if you've got a muscle that's called a flexor, like we said, you know where to find it, or where you should expect to find it. Now, don't let yourself get super confused with the cadavers, because the cadavers do not preserve an anatomical position, right? They just don't, because anatomical position doesn't feel very natural, right? And you would actually have to hold them and strap them down. So where do you look for flexors? Well, you find the wrist, right? You find the anterior surface and you look for the flexors there. Okay, does that make sense? So you're going to look for the flexors not like anterior when you're looking at the cadaver in the tank, anterior relative to anatomical position. Okay, so flexors and extensors, abductors, adductors, pronators, supinators. So sometimes they're labeled that way. Sometimes they're labeled or named by the orientation of their fibers and fascicles. And you may not know the term fascicle yet, but let me show you what I mean. Okay, so this muscle is called the rectus abdominis, right? And the rectus abdominis is called that for two reasons. Any muscle that's called a rectus will have fibers and fascicles that are running parallel to the long axis of the body, because rectus, or erection, means straight up and down, right? Okay, so you have a rectus abdominis muscle, which is telling you that the fibers are running straight up and down in the abdomen. Okay, that makes sense? You also have a rectus femoris muscle, and the fibers are running straight up and down over the femur. Okay, or even though this terminology is slightly different, it's pretty similar. Where are you? These are the erector spinae muscles, right? Because the fibers are running straight up and down right next to the spine. Now, just so you know, you're not actually seeing the fibers. You are actually seeing fascicles. We haven't talked about that yet, but muscle fibers are microscopically thin. You can't see an individual muscle fiber, but you can see bundles of muscle fibers called fascicles. So that's actually what you're seeing there. It's running the same direction as the fibers. It's just a bundle of them that's actually visible with the naked eye. Okay, so you have rectus muscles. You also potentially have transversus muscles. And a transversus muscle has fibers that are running perpendicular to the long axis approximately. And so I think the only transversus that you guys are going to learn is the transversus abdominis, right? And fibers run approximately that way. So you have a rectus abdominis and you have a transversus abdominis. Okay? And then some muscles do not have fibers that are running parallel or perpendicular to the long axis of the body, but they're running at some other angle. Like you have external abdominal obliques, okay, and the fibers run this direction. You have internal abdominal obliques and the fibers run that direction. So sometimes they're named by the direction of the fibers. Is that okay? Okay. Sometimes they're named for specific body regions, which is part of the reason that I had you learn all of that terminology about the body regions. Because if I have a muscle called the brachialis, I know where to look for it, right? If I have a muscle that's called the rectus femoris, I know two things about it, right? Straight up and down over the femur. Where would you look for the intercostal muscles? Between the ribs, and that's exactly where they are, between the ribs. How about the frontalis muscle here, occipitalis, temporalis, right? Now, sometimes they're labeled for where they are with reference to one another. So I have three vastus muscles. I have a vastus lateralis, an intermedius, and a medialis. So it's like position with reference to one another. Does that make sense? Sometimes the position is like this. I have a superficialis and a profundus. What is that telling you? Yeah, so superficial and profound or deep. Yes, so it's trying to tell you the relationship of the two muscles with reference to one another. Is that okay? Okay. And then sometimes they are named by shape. A deltoid muscle is super easy. I mean, everybody knows where it is anyway, but it is also what shape? Triangle, a delta, yeah. Trapezius, how much geometry do you remember? What's the shape of a trapezoid? What is it? Yeah, what is the trapezoid shape? Yeah, it's quadrilateral, but not with right angles, right? Not with 90-degree angles, usually kind of diamond shape. This, I don't know why I have such trouble with this. I get the trapezius and the latissimus dorsi confused constantly, ever since I was little. And the only way that I remember it is because the trapezius goes here to here to here, and it's shaped like a big diamond on your back. That's the trapezius. And the latissimus dorsi isn't. It's like wings coming out to your humerus. That makes sense? Okay, so that's the trapezius. And then you haven't learned this muscle yet, and most of you probably haven't heard of it before, and it's called the quadratus lumborum. It's trying to tell you two things about the muscle. What? What shape? It's four sides, right? So it's a little rectangle. And where is it? In the lumbar region, right? Quadratus lumborum. And then sometimes they're named by their relative size. A maximus and a minimus, sometimes a medius too. Do you know any maximus and minimus muscles? Gluteus maximus and minimus, yeah. So sometimes also major and minor, right? Big and small. I mean, they're not consistent with maximus and minimus. You know what a major and a minor? Teres. Pectoralis. Yes. Okay. That makes sense. Okay. And I'll get to brevis in just a second. Sometimes you have a longus and a brevis. What is longus and brevis? Long and brief, right? Long and short. Here's something that you need to understand because it's really confusing otherwise. Longus and brevis does not refer to the length of the muscle. It refers to the length of the tendon. So it can be completely counterintuitive. If, for instance, you're looking for the long head of the biceps brachii and you look at it, you're like, that one's shorter because the muscle part of it actually is short, but the tendon part of it is longer. So whenever you run into long and short heads or longus and brevis, it's referring to the length of the tendons, not the length of the muscle. Does that make sense to you guys? Okay, so the longus and brevis can be useful. We have fibularis longus and brevis, and we've got long heads of things. We've got longus and brevis muscles, a bunch of different places, and that's generally what it's referring to as the length of the tendon. And if you get that, you'll be way more confident in lab than other people because they'll be like, I don't get it. You're like, oh, it's the length of the tendon, and you'll feel brilliant. Okay. Now, they didn't ask me, but if they had, this is how I would have labeled all muscles. Some muscles are labeled by their attachment points. And when they are, it's always origin before insertion. So for instance, if you find a muscle that is called the brachioradialis, you know that it goes from the arm to the radius, so you know to expect it lateral, right? And then all you have to do is figure out which side of the joint that it's on, and then you kind of already know what it does too, right? You're like, oh, okay. So that would be an amazing way to label all the muscles, but they didn't do that. How about the sternocleidomastoid? It is labeled two origins and then the insertion, right? Sternum, clavicle to mastoid process of the temporal bone. okay? And that means that if you got it strapped up that way, you can figure out some of the actions. It depends on whether you use both heads of it or one head or whatever. So it can do several different things. That make sense? Okay. So sternocleidomastoid. Whenever you've got regions, it's always origin before insertion. Okay. Good. Okay. And then number of origins. Okay. So let's talk about that. Sometimes a muscle has more than one origin sharing a common insertion point. And that means that the muscles can work together to do at least some of the same actions. But do not be surprised if the one that's slightly more lateral has some lateral functionality that the one that's medial doesn't. But they're going to have some overlap of functionality. So a muscle that is called a biceps muscle, and we've got two sets of biceps muscles. We've got the biceps brachii muscle, and we've got the biceps femoris muscle. The biceps muscles have two origins sharing a common insertion, which means they're going to have at least some commonality of function, right? That makes sense? So biceps means two heads, okay? A triceps muscle, three heads sharing a common insertion, right? Make sense? And biceps femoris is back here, two heads sharing a common insertion. They're going to have overlap of functionality. And then a quadriceps. This is not actually a muscle, it's a group of muscles, but it's called the... Somebody complain about that. When I complain, they don't care, but if students complain, they do care. So they're like, oh my God, you're complaining again. Okay, so the quadriceps femoris group is four muscles that share a common tendon of insertion. And so they're going to have a lot of overlap of functionality. Does that make sense to you guys? So that's what quadriceps means. The good part about that is if you know that they share a common insertion, you do not have as much to memorize. You're like, I wonder where the biceps femoris inserts, the long head and the short head. Same place. Where's the quadriceps femoris insert? Same place. Right? That's like by definition, they insert in the same place. Is that okay? Okay. All right. So I want to try a couple of hard ones, and then we'll do some easy ones. So if you are going to run into the flexor carpi ulnaris and the flexor carpi radialis, I want to talk about expectations as to where you expect to find them. What is flexor telling you? Anterior surface. Carpi should tell you that it should cross what joint? Should cross the wrist joint. And the ulnaris versus the radialis. Yeah, so which one's going to be more lateral? Radialis. And the one that's going to be more medial is going to be the ulnaris, right? Okay. Extensor digitorum. Do you know where your digits are? Whether it's longus or brevis. If I have an extensor digitorum, then is it going to cross just this joint, or do you know that it actually has to go further? Right? To extend the digits, I have to be able to do this, right? If I'm an extensor carpi, I do this, yes? But if I'm an extensor digits, I can go from here to that. Does that make sense? So it's telling you it's going to be on the posterior side, and it's going to have to go all the way down. Does that make sense? You also have an extensor digitorum down here, right, in the leg. You've got a longus and a brevis up here. I don't know. Did you have to do both longus and brevis? I can't remember. Longus and a brevis up here, and then just an extensor digitorum there, down there. Not a longus or a brevis. Is that okay? Okay. Let's see. Okay. Now these are easy ones. Tibialis anterior. What's it telling you?
The tibia.
Anterior tibia. Temporalis is here. The erector spinae. It's telling you it's straight up and down next to the spine. The triceps brachii, and I know you know this one, it's telling you two things, though. What's it telling you? Three heads and on the arm, right? Okay, that makes sense. Flexor carpi radialis, anterior across the carpals, lateral side. Yeah? Okay. Extensor pollicis longus, telling you three things. Back side, moving the thumb. What can you tell me about the tendon? The tendon's going to be long. Exactly. That makes sense? So when I go through each of the muscles, I like to try to figure out why they're named that so that I can use it to like help me bring it up when I've got a blank piece of paper, right? Because you do during the lab practical. Is that okay? Okay, do you guys have any questions? Okay. Everybody okay? For sure? Okay. So does that make it sound more doable? Right? It is more doable once you realize that it's not just a bunch of rote memorization. There is actually a lot of logic to it. But it's just like everything else, you can't really start to understand it until you stop being freaked out by it. You're like, oh my God, oh my God, oh my God. It's okay. It's okay. Like, right? When you feel overwhelmed and you've bitten off more than you can chew, you just keep chewing. Just keep chewing, man. Just keep chewing. Like, it's gross to think about with muscles, but okay. Okay. So now we are going to change gears a little bit, and we are going to start talking about muscle tissue again. Now, the stuff that we just did is going to correspond. I'm super irritated by that. The stuff that we just did is going to correspond directly to lab, and I'm going to reinforce it with quizzes, and we're going to be talking about it. The stuff that I'm about to do corresponds to physiology. You have to go all the way down to the tissue level and below in order to start talking about how muscles actually cause movement. Okay? So this stuff you won't be quizzed on in lab. I do expect you to know it in excruciating detail, because when you get to physiology, they start talking about functionality, but they don't teach you anatomy again, right? And so for poor souls like this, who took physiology before anatomy, because she really likes challenges in life, they start talking about how to move muscles without teaching you what the sarcomere is and what actin and myosin. They just like go from there. So I don't know how you're going to experience that. When I teach physiology, my notes all have a before you begin section that has the go review this anatomy, go review this chemistry, and go review this cell biology before you come to class, so that I can make sure everybody's ready. But not everybody does that, all right? So you're going to have to know this deeply, even though you're not going to actually be reinforcing it in lab. Okay, so characteristics and functions of muscle tissue. How is muscle tissue the same and different from other tissues? First thing is that muscle can respond to an electrical stimulus. So if you get electrocuted, what happens to your muscles? Right? So it responds to an electrical stimulus. Now, electrical stimuli are made naturally in your body by mechanisms that are very hard to explain until you take physiology, but they are. And then what muscles do upon electrical stimulation is they contract. And muscle individual cells, and these are the only tissues in your body that do this, will actually shorten upon stimulation and then relax back to their original length. What they're really doing is they are converting chemical energy in the form of ATP usually to mechanical energy or kinetic energy, yeah? And you should remember from chemistry or 1610 that energy conversions are inefficient, right? And what is generally lost whenever you convert energy? You lose energy as heat, exactly, which is one of the major reasons that you can use your muscles to heat up your body temperature, right? So if I'm really, really cold, I will have involuntary contraction of my skeletal muscle, right? And that's shivering. And it's dramatically effective at increasing your body temperature because of this. Because this energy conversion is inefficient. Heat is always released as a byproduct. Okay, muscles also have extensibility and elasticity. So muscles are not just muscle tissue. There's also connective tissue wrapped all in them, and the connective tissue has mostly collagen fibers, but also some elastic fibers in it. And so what you can do is with a muscle, you can stretch the connective tissue associated with the muscle, but it doesn't become flaccid when you stretch it. Otherwise, people who did yoga would be, super floppy and have absolutely no muscle tone. That's not true, is it? So if you can stretch it, that's extensibility, but it also has the characteristic of elasticity, meaning that you will return back to your original shape. Now, what does the stretching do? It generally increases range of motion. It stretches the connective tissue associated with the muscle so that you can increase the range of motion. It's not changing the muscle tissue itself dramatically. It's just loosening up the connective tissue associated with the muscle. And there's tons of connective tissue associated with the muscle. And then I just want to remind you that now we're doing muscle in this set of notes. We're going to be concentrating on skeletal muscle. At the end, we'll do smooth and cardiac. But you are going to be responsible for that table over muscle tissues again. Striated, how many nuclei, functionality. So I'm not saying you're going to have 20 questions about it, but you might have 2 on your test, because I don't want you to forget histology when we move on to gross anatomy. So you're going to be responsible for that one more time. Okay, so let's just talk a little bit about functions of muscle tissue, and then I'll let you guys go. So muscle does obvious things. It does motion, yeah. Skeletal muscle mostly moves your bones around, but not exclusively. Smooth muscle moves things through tubes, and cardiac muscle, of course, generates pressure to move things through the cardiovascular system. But you're not always trying to move things. For instance, skeletal muscle also does posture. If that doesn't make sense to you, then ask yourself whether I could be sitting up here if I were quadriplegic. I couldn't be sitting here unaided. So postural stability requires muscle contraction, right? Ab, back, neck contraction. Does that make sense? In addition, muscle, I already told you, helps stabilize your joints. When you strap a muscle across a joint, it stabilizes the joints. We already talked about heat production. Muscles actually keep your fluids moving. The obvious ones, like smooth muscle in the wall of a tube, will keep fluids moving. But cardiac muscle also keeps your fluids moving. But I don't know if you guys know this, skeletal muscle also helps keep fluid moving, because if I've got blood vessels, the veins in my legs are super low pressure, and they have a really long way to go, not that long in me, but proportionally. They have to go all the way back to my heart, and they're very low pressure. So how do I keep the fluid moving? In addition to the smooth muscle in the walls of my vein, every time the skeletal muscle contracts, it actually squishes on that vessel and helps keep fluid moving. So when you're more active, you not only do that have better arterial flow because of what your heart is doing, you have better venous flow because of what your skeletal muscles are doing. Does that make sense? And then guarding openings, sphincters. You have skeletal muscle sphincters that you can control at the bottom of your digestive and urinary tract. You have smooth muscle ones all internally, like things flowing. And then the last thing is that sometimes muscle is more about support than it is about movement. For instance, the abdominal muscles, in addition to doing the moving, they also are, if the abdominal muscles have tone, they're squishing your organs up back against your body wall. If you lose muscle tone, like you had to have an emergency surgery, an emergency C-section, if you don't have an emergency, then they'll carefully separate the muscle fascicles and try not to rip them. But if you have to have emergency surgery, like you're about to die, they're going to slice right through them. Can you see how losing the structural integrity of the muscle could end up making you have a pooch, even though you don't maybe have any subcutaneous fat to speak of? Does that make sense? So you get that little pooch, and sometimes it never goes away, right? The other place that's really important is here. You have your pubococcygeal muscles that hold your junk up there, okay? They hold your urinary bladder up there and your uterus up there. And keeping those in shape is really a good idea. It helps to put off urinary incontinence, okay? For males, it helps to maintain erections. And very importantly for females, if you have a whole bunch of big-headed babies, you can completely destroy the structural integrity of your pubococcygeal muscles. And then you can get uterine and urinary bladder prolapse, and they just flop out. Okay. That's some good birth control right there. They should use that crap in those abstinence-only education. Junk falling out, right? Yes. Okay, we'll stop there for today.
That can be fixable, right, Melanie? Mommies will have